Greetings from my kitchen cell phone studio in Savannah, Georgia. I'm going to talk today about a phenomenon called Japan Law twinning and a mystery that has not been adequately researched, which is how Japan Law twins get started. What you see here is a Japan Law twin. Its C-axis between the two crystals are at an 84-degree angle, and they have a contact between them. How does such a twin get started? Well, one way of looking at it is to take two quartz crystals, take a crystal like this, which has the 6 rhombohedral faces toward the termination, and between the 2 rhombohedral faces there's an edge, and if you put the two crystals edge on edge, you get what is essentially a Japan Law twin. That's the angle between the two C-axes. The problem is, to start one with these edges means that they are in a very unstable position to grow and develop into a Japan Law twin. Now, Japan Law twinning is described as having a plane straight across the twin between them, which would be the plane that would be evenly between the two faces, and that's the 1-1-2 plane. Quartz enthusiasts have a problem with this because quartz rarely produces a 1-1-2 plane. In fact, in the last book that Akira Tsunegawa wrote, which was about the morphology of quartz crystals, on page 124, he came to the conclusion that it is unlikely that two individuals bounded by well-developed faces conjugate on a 1-1-2 face to form a contact twin after the Japan Law through the growth process, since 1-1-2 cannot develop as a well-developed flat growth face. So that presents a dilemma. How do they form? Now, Tsunegawa suggested that they would form on two rhombohedral faces, like so. But the problem with that is that produces a twin angle of the Reichenstein-Griesenthal law twin. He didn't get to explain too well, and unfortunately he's died since then, so he was never really able to develop it, but he thought that they would form this way and through dislocations get to the point where they were locked into the Japan Law twin. I thought that was an interesting suggestion, but if you take, and I discovered and reported this a couple of years ago at the symposium, if you take two quartz crystals aligned and you rotate them 180 degrees around those rhombohedral faces, axis perpendicular to them, you get the Reichenstein-Griesenthal law twin. But if you only rotated it 140 1/3 degrees, you'd end up with the Japan Law twin. And that works kind of nicely, except for one problem. How do you get, what kind of way does this contact work? If you look at it end on, you can begin to see that there's no straight plane across the twin. It's an angle in the middle there. And that raises the question of, is there structure, atomic structure, the way the atoms line up, that is compatible with that point of rotation between the two crystals? Do they line up fairly well to make the twin, and is preferable? That's not anything that I'm equipped at my age and my education to jump into and figure out. It's a fairly complicated process to model the atomic structure of the crystals and then line them up and take into account various things like relaxation on the surface of the crystal. And I can talk that but I can't do it. It's interesting, though, if you take this Japan Law twin and you look at it, you can see that there is that same angle in the middle of it, which suggests that maybe that is the way Japan Law twins develop. Now, Sunagawa also suggested that Japan Law twinning started with bipyramidal crystals. So I have gone and gotten some bipyramidal crystals. These are beta quartz crystals, and which make nice bipyramids, and you can put them together, rhombohedral face on rhombohedral face, and you get the equivalent of a Reichenstein-Griesenthal twin. And you can put them edge on edge, and you get the beta quartz equivalent, and if it would be the same if it were alpha quartz bipyramids of the Japan Law twin. And you can even, as you can see looking end on, you can slide them down and have a contact surface where they could be fixed and they could grow from there. So it's essentially the same as what I was showing earlier. Now, recently I ran across a paper by a fellow named W.A. Tarr. You've probably never heard of him because this paper was written back in the late 1920s. It's in volume 14 of the American Mineralogist. And he's talking about quartz crystals that have been found in gypsum beds in New Mexico, which describes pretty much the locality where a lot of pseudocubic quartz has been found. And he's talking, he points out that in these a chunk of gypsum, he found that there were several crystals, and he said a study of those small crystals, there were some very small ones, revealed the sequence and development of the faces of the crystals. The very minute crystals were the plus rhombohedron. That's what we would call pseudocubic quartz, or it's a simple rhombohedron which has 6 faces. It's almost like a cube, except it's like a skewed cube, and they had high luster. And this was the only form on the crystals until it attained a length of 0.15 millimeter. That's pretty small. And then they began to develop the minus rhombohedron Z. And with increase in size, the minus rhombohedron grew faster, and by the time the crystal was 0.5 millimeter long, both faces were nearly equally developed, resulting in fine, small, he calls them quartzoids. It's the bipyramidal quartz crystals. So at that point, I said, I've tried putting crystals like this together. I've tried doing it with the bipyramids. How about doing it with some pseudocubic crystals that are mostly simple rhomb, and they came from the locality that actually Mr. Tarr was talking about. And I put these together, and this is the equivalent of the Reichenstein-Griesenthal twin. And it's, if you start angling them differently, it's kind of hard to figure it all out. And I got a little frustrated with trying to see what happened there. So I started drawing in shape, and even in shape drawings, I had difficulty figuring out things. They looked kind of strange. So I had one that was a pseudocube, a simple rhombohedron, and then I put it on a crystal, like this crystal, and when I did, the edge of the rhombohedron lined up with the edge between the prism and the rhombohedron on the other crystal, and since that side is parallel, the side that is lined is parallel to the other side of it, and it'll land with the edge of the crystal. And that got me to thinking, what is going on here? And what I came up with finally is represented in this model, where I have a large quartz crystal, and then I have another crystal that I mounted on it. And basically what I'm trying to model here is that on this larger crystal, it has the rhombohedral face here, but all the striations on most quartz crystals, the little lines that go across the prism faces, are parallel slivers to the rhombohedral face. So this is representing a big rhombohedron edge of a striation. And I take this little pseudocube and I put the edge in that notch. It lines up very well that way, and then I lean it over, and when it's leaned over with the rhombohedral face to the rhombohedral face, suddenly you get something that is almost exactly the angle of a Japan Law twin, which means that this is one way a small crystal landing on another crystal can be oriented and fixed in a way to develop into a Japan Law twin. I drew this using shape, and the red line that's parallel or horizontal is a line that's parallel to the c-axis of the big crystal, and the line that's almost vertical is the c-axis of the ROM. And I manipulated it to the angle where these two axes are in the plane of the sheet of paper, and you can see it has almost exactly the Japan Law twin angle. So it may not explain how the V twins get started, but it probably is a good explanation for how Japan Law attached oriented twins get started. That's a term that Nespolo uses to describe how you can get a small crystal growing on an already established crystal that it has a Japan Law orientation and has all the Japan Law growth features, like the exaggerated growth in the notch that makes it more tabular. And you can see here on these two crystals from the same locality in Colombia that it can be, the attachment can be oriented so that the Japan Law angle is oriented toward the top of the host crystal, or it can be oriented so that the Japan Law attachment is oriented toward the base of the host crystal. I think this explanation, this model that I've developed, may be a way to explain how that happens. The question now is, does it really work that way? This is just theory. It's a suggestion. I wish I could tell you more, but I do hope that somebody might explore and maybe find a way to produce little small ROMs and see how they might orient if they land on a larger crystal. I would hope that somebody would do some modeling to see whether there is some kind of a favored atomic structure orientation across a twin boundary where these two rhombohedral faces are land on each other. At this point, this is only a speculation, and I'm open to questions to anybody who wants to talk about it. And hopefully there will be some research that's done to eventually find out how these things get started. Thank you.